The big red is.
Oh, nice.
That is.
There's snow, right?
So,
That's true. And we finished summer.
yeah, we should.
I asked because I went on a bachelor party last year to Maine when it was really snowy. And we got snowed in. Ended up being awful. We had to dig our car out. We couldn't snowboard because they closed the mountain. Yeah, it was overall not a great experience. So wish that on any. Although we have a ton of stories to tell now because of all that.
I don't think they have any.
That's good. Roads will be clear, no chains or anything like that, so it's good.
Yeah. This is surprised when I walked in. The people there.
You guys running a cabin up there?
I don't think I got these getting. Exactly.
Oh, okay.
All he says, getting an Airbnb
Nice.
and stuff. All I need to know is whose house am I meeting that time? But yeah, those are good questions.
Good to know.
Yeah. So I need, once I know that, I just now gotta take my golf clubs and go and golf.
Nice. Nice. Do they have golf up there?
They have an annual,
Oh. Must be beautiful.
I don't know, I'll find out. I'll report back next week.
I mean, I'm not much of a golfer myself, but my dad and my uncle love to golf.
And then the original plan was to go on the lake on Saturday, but. Lots of people over to really high, so all of it. So it's like, oh yeah, we'll take the ski lift up to the top and then drink and then hike down.
Sounds like a good plan.
But yeah, great. What could go wrong? Instead of that. It's kind of nice that we only have, we're able to charge at these desks.
Oh, charger. Oh, yeah.
It's CS309 has the had to begin with.
They don't have any.
No, they still do. But I never had a class in there.
Oh, I see.
And so last year and then this semester too, when I was in here a lot. Everything really is. The one thing I'm running this stuff, you actually being here in class now physically, getting the text from outside.
Always a good thing.
Yes, not eating dinner well. That's true.
My sister actually just moved back in there. Can't really do that when you can't be the wife with your parents. Usually not a good idea.
He's been working out for my brother.
Okay.
He was in all of the world. We knew that even before we got married.
Okay. Yeah, first activity should take.
Oh, no, not for last.
Oh, up in the day. Oh, yeah.
Should take it too. But you're going to do that one I'm stuck on how to do it on Excel. Another strings that just took me on.
Oh, nice. You can approximate too, it doesn't have to be an exact round. Just draw something that's.
And then we probably call it like that. Yep, we can- Right. Taking long to get that.
Those ones I sort of.
Everything else like that.
Okay, that's good. That's all I care about. That's all I can read it. Good.
No, I think we have to allow it.
It's an issue for some people, it's really hard. It's like, I want to give you credit. I can't understand what you're doing.
I did that to.
Um,
And then for our midterms and finals. We get us. No one. I'll do it in pencil first. Make so I didn't see how to do it.
yeah, that works.
It's so light. What I do. It applies all.
It helps.
Basically.
Yeah.
Because I read so light, I actually use the 0.3.
Oh, wow, that's pretty good. Even with the 0.7, I still break them in like. I pushed down for the version. Wow.
If you've done 0.3.
3D.
Thanks.
Oh.
Without, I right, with everything that blurs together, it's bigger.
Makes sense.
Yeah. And ours and hers. After almost, after 2.5 hours, actually after 2, so I was 45 minutes, we're still battling 19.
Oh, wow. That's a long time.
It's pretty good. House the last graphic. Funny to go over. Yeah. So. Okay.
Oh, yeah, I think so, okay.
Good. They're struggling. Oh. These are just graceful. See.
Yeah.
You take it out?
Yeah, they're not.
Oh, wow, do the same. I brought something for a while. My girlfriend left at like 2 o'clock.
Yeah.
Set your alarm. So I first place. I did set an alarm. I woke up to her opening. Sure. It's like, it was like 4 something. It's like 2 hours. How cold. This was like a good enough. Oh, this was like tonight. Go back to zip it using the entire itself out.
I this is a.
It's like an outside, like a special, and there's someone that can dip more.
Yeah.
Exactly. Yeah, special. And you can dip it. Yeah, so you dip it yourself, it's not going to.
Yeah. Oh, yeah.
It's okay, everyone goes through it at least.
Yeah, okay, that makes sense.
It's really annoying.
I was like, I zipped it and there's nothing in this folder now.
That's nice, yeah.
Clicked on it also.
Okay, that's good. Yeah, if we're working on the same computer, then it's fun.
Yeah.
Like I kind of char the tomatoes, just like on both sides. And I fry the garlic, and then I put it in the oven.
I was just like,
One glass
oh, yeah?
of it. Yeah. And then I do that for some fun. And I can make
All right.
Okay, it's 5:30. Let's go and get started. All right, good evening, everyone. How's everyone doing today? Hopefully everyone had a good long weekend. Okay. And hopefully all the waitlist situation is settled. So, I apologize that it took so long, but it seems like people were able to use the permits on Friday. So I think everyone's had to the class. Is there anyone still on the waitlist for the class? Okay, all right. So yeah, I talked to Kevin who works in our office. On Friday, he said people were using the permits, and so it seemed like it was working. So hopefully all that is everyone's in the class, they're on canvas, and you can just go kind of full speed ahead. Okay. All right. So I changed our plans a little bit this week. So Thursday we're still planning on having our next ANSYS activity. So Thursday is going to be activity 2. So my original plan for today was to do a little bit more review on strength of materials, specifically on beam theory and how beams work. But before the next activity, I really wanted to go over a little bit of meshing, just because that's kind of the biggest question mark in terms of how we do FVA. And so I'm kind of changing the order of things a little bit. So I'm gonna talk about meshing today, just so that you'll have that knowledge before Thursday, and hopefully it'll make some things make more sense on Thursday. Okay. All right. So just to kind of recap, Thursday we're doing activity 2. It's just that we're not we're kind of skipping ahead in the class. So we're talking about meshing today, and then next week we'll talk about boundary conditions and material properties. Okay. So I think that's all my announcements. I haven't posted activity 2. I will do that for Thursday. So I'll probably do it sometime tomorrow morning, just so you'll have it. And then Thursday we'll. All right. Any questions I can answer for the class before we get started today? Okay. All right. So let's go and get started. And so the title of the lecture today is meshing basics. Okay. All right, so meshing, hopefully this is a step you remember from activity 1. So we kind of talked about it briefly then, but I wanted to kind of go over it kind of in more detail today. All right, so first let's define meshing, and so meshing, at least within the context of finite element simulations. Meshing is the process of taking some kind of complicated geometry and breaking it up into a lot of simpler geometries, usually with a fixed shape. And the reason we call it meshing is that visually, when you look at kind of the finished product, it looks like you've added kind of a mesh grid on top of your structure. Okay. All right. So this last point here, of making sure all these simpler geometries have a fixed shape is really important, and that's kind of key to the whole finite element simulation. And so we'll go over the different types of shapes that are available, at least within ANSYS, and kind of the pros and cons of each shape, because you do have some flexibility in terms of how you choose them. Okay. All right, and so this is a necessary step. So before we run any kind of FEA simulation, we have to do meshing because this is the step that basically allows us to solve the complicated differential equations on our geometries. Okay. It's a little bit difficult to describe exactly how it works in kind of a couple sentences. If I had a couple lectures, it would be a little bit easier. But kind of the nature of this class, because we're kind of focusing more on ANSYS, it's a little bit kind of hard to describe how it is, but I'll kind of do my best. All right. And so kind of the basis of FEA and the reason it works is that we're not when I say we're solving differential equations, that's a little bit misleading because we're not solving for exact solutions, right? What we're doing is we're approximating the solution for the differential equations on our geometry. We're looking for an approximate solution, and this is a lot easier to do when the shapes that you're working with, exactly how many sides, how many corners, how many vertices are on those shapes. And so let's say that, let's pick just a very common FEA shape, let's look at a square, okay? Or I should say a rectangle, kind of be a little bit more generic. Okay. So a rectangle can come in, lots of different flavors, right? And so we have one that kind of looks like a square here. Okay, we can have ones that are more kind of narrow. We can even have some that are more skew. Maybe something looks like this. Technically, that's a four-sided, four-sided polygon, right? So it's a rectangle. Or I guess if you really, for the geometry buffs out there, technically that's quadrilateral, right? But what do these four shapes all have in common? They all have four sides. They all have four corners, right? And so we can use that to our advantage when we're approximating the solution of a differential. As opposed to the opposite. So let's say that we have a very generic geometry, right? So let's say we have something that looks like this, right? Completely generic, I literally just scribbled on the screen right now, right? Ahead of time, we don't know how many sides, how many edges, how many corners there are to this thing. So, this would be very, very difficult to solve, the differential equation, right? So you don't know exactly what's going to happen. But if we take this geometry and we break it up into rectangles, right? We may have to use a lot of rectangles to do it, but if we but in theory, every little rectangle is a rectangle, right? So if I were to put a mesh on this thing. Instead of having one very weird, complicated looking shape, we now have a bunch of very, simple shapes that we know exactly what they look like, right? And so instead of that, we can say that we can solve our differential equation on each of these rectangles individually. So that's really the key. That's really the key to, of why meshing is important. Is to take a geometry where you have no idea, what it may look like beforehand. It could have, countless number of sides, and to kind of break that down into lots of smaller shapes where you do know the dimensions beforehand, and you do know how many sides, corners, edges, things like that. And that's kind of the key. Okay. And so meshing is the process that we use to accomplish this, right? And so when we say that we're going to put a mesh on a geometry, it means to produce this origin. Okay. And so, one notion I think when a lot of people who are first starting FEA think of is, they try to find the perfect mesh for this geometry, right? So what's the perfect looking mesh? There is no perfect mesh, right? And in fact, there are literally infinite different ways that you can mesh a geometry. And so, I want to kind of, make it clear now that, when you're meshing an object and you're trying to find, a good mesh to use, you're not looking for some perfect, mesh, right? There are better meshes than others, right? So there are some meshes that, are going to give you a better quality solution than other ones, but there's no best mesh. And so what we're going to talk about today is just some of the basic kind of characteristics of a mesh. What produces better meshes than others, what you should look out for in a mesh, and just a lot of the settings that you can use to modify your mesh. Okay. And so another thing too is that meshing just by itself is a very, very rich topic. And so we can talk a lot about meshing, and and this is not the last time that we're going to see meshing. And so the purpose of the lecture today is just kind of give you an introduction of the basics, just so that when we're kind of playing around with the settings on Thursday and in the future activities, you kind of understand the context of kind of what we're doing, and just so that you start to gain some intuition of kind of looking at certain meshes and seeing that's a better looking mesh than something else. Okay. But we'll see meshing kind of come up, multiple times. In fact, this is probably the topic just in general that we cover the most in this class, is how to get a good mesh. Okay. ANSYS makes it look very easy, and in fact, all the activities that we're going to do will make meshing kind of look almost trivial. But if you ask any kind of professional engineer, probably what they spend the most manual time on is trying to get as good of a mesh as possible for their projects. Okay. Because as the geometries get more and more complicated, it becomes more and more difficult to get a good quality mesh. Okay, any questions on this so far? Okay, all right. So let's jump in. So let's talk about what makes a good mesh. So what makes one mesh better than the next? And so to talk about kind of what makes a good mesh for a bad mesh, I want to talk about kind of two main qualities or two main characteristics of of your FEA simulation in general. Okay. And so the first thing that we'll talk about is accuracy. Because ultimately, the goal of your finite element simulation is to perform a simulation or an emulation of some realistic process, right? And so ideally, you want your simulation to be as accurate to the real life thing as possible, right? And so, your mesh is probably the number one determinant in terms of how accurate you're going to be. Okay? And so you want your solution to be accurate, but you know, you also want your mesh to give you the results at a good cost. Okay. So computational cost refers to, you know, how much computer memory, how much computer power it takes, or kind of in more realistic terms, you know, how long it takes for your simulation to run. Okay. And usually these two qualities here, accuracy and cost, are kind of counterbalancing each other. Right? And so if you go for a highly accurate simulation, you're going to pay a lot of cost. If you want to go for a really cheap simulation, you know, probably your simulation may not be as accurate as you can. All right, so let's go into each of these in more detail. All right, so let's talk about accuracy first. So like I mentioned, you know, when we talk about accuracy of an FEA simulation, it refers to how closely your simulation replicates the real life scenario it's trying to emulate. So this is really important, right? Because you know, most of the time, you know, at least in our context, we use finite element simulation to perform, you know, engineering design and analysis. Okay. And so the usefulness of an FEA for those processes is really only as useful as it is accurate, right? And so your simulation needs to have at least a certain degree of accuracy to be useful for engineering. With FEA, you know, we're trying to get realistic results, right? And so, you know, we're not just looking to produce kind of pretty images, pretty figures. You know, you want something that's going to predict, you know, what the deformation is going to be, what the equivalent stress is going to be with a certain degree of accuracy, right? And then you can use that information to inform your design in terms of, you know, how you can make your design better or more safe or whatnot. Okay. Okay. So how does the mesh affect accuracy? Well, the mesh affects accuracy in a lot of different ways that we'll talk about. But I think the main thing that I want you to get out of the lecture today is the correlation between element size and accuracy. Generally, as the element size goes down, right? And so as generally as your elements get smaller and smaller, then the accuracy of your finite element simulation will go up. So remember I mentioned earlier today that, FEA, what we're doing is we're computing an approximation to the solution of the differential equation, right? And so one way that you can kind of think of it as, for each element kind of approximates the solution of the differential equation in that area that the element occupies. And so the smaller your elements are, the more accurate the approximation can be, because then, you have several different elements or lots of different elements to approximate the solution, as opposed to maybe just one big element. Okay. Right, so a good analogy that I like to use for this situation is to think about image resolution, right? And so, if you're looking at a digital image, or even if you're looking at, maybe you're watching sports on a television, right? Generally, the more pixels that you have in the image, the more sharper and more clear the image is going to appear. It's the same way with FEA, right? And so the more elements that you have in your simulation, you can almost think of that as adding more pixels to your to your image. Okay. And so the more elements, the more pixels, the more accurate your simulation is going to be. And so, like I mentioned, there's more factors that affect the accuracy of a simulation than just the size. But if I had to rank all the different factors of a mesh that affect the accuracy, size will always be number one. Okay. And so that's always the first thing that you should think about, when you're running your simulation, is how big should my elements be? And what effect does increasing the number of elements what that has on my simulation? All right, any questions on this? Okay, so that's element size, or accuracy, excuse me. Let's talk about the other factor, computational cost. All right, so when I talk about computational cost, I don't directly mean cost in terms of dollars and cents, right? Computational cost refers to the amount of computational resources it takes to run your simulation. Eventually, it does get translated into kind of real dollars and cents in terms of the power bill, it needs to run your computer. But we can talk kind of way before then. And so the main computational cost that at least people tend to notice when they run their simulation is number one, the amount of time it takes to run the simulation. And number two, the amount of memory in your computer it takes to actually, store the result and display it and things like that. And so how did the mesh affect computational costs? Well, we just finished learning that, as your elements get smaller, it's going to increase the accuracy of your simulation. Okay. But the smaller you make your elements, it will then require more elements to actually approximate your geometry. Okay. Because you can almost think of your CAD geometry as having a fixed amount of volume, right? And so if your elements are smaller, right, it's going to take more of those elements to fill that entire volume rather than if you had bigger elements. Okay. But the more elements that you have in your mesh, the longer it's going to take, or the more computational cost it's going to take to actually run the simulation. Right. So you want highly accurate simulations, but it always costs something, right? And so there's a saying, you could apply this to almost anything in life, but there's a saying that there's no free lunch, right? And so you can't have a highly accurate simulation without paying some kind of cost. Okay. Of course, you can be clever with how you allocate those elements, and you can mesh in kind of an intelligent way where you kind of get more accuracy for the least amount of elements. And so we'll talk a lot about that. But generally speaking, if you want more accuracy, you got to pay more cost. One note that I'll make though is that you might have this notion by the end of the class that the notion of cost doesn't exist. Okay? Because all the simulation we're going to run in this class are very, very low cost simulations. So, when I say your cost is increasing, that may be the difference of your simulation taking 2 seconds to run versus 7 seconds to run, right? And so it's a very negligible difference. So, if you're waiting 7 seconds, that's like nothing. And so for this class, it's kind of difficult to kind of get a sense of how high the cost can get. But trust me when I say that, when you get to kind of more practical FEA and the number of elements in your mesh reaches, in the tens of millions, hundreds of millions of elements, it makes a big difference, right? And so sometimes it could, maybe if you mesh a little bit more intelligently, it can mean the difference of your simulation taking only a day, an entire day to run versus an entire week. Okay? And so it scales up very quickly. It's just in this class, we don't really see it that much because of the limitations of our license. Actually, in the world of practical FEA, at least for what I worked on in research, it's very common to actually run your simulation on a supercomputer or supercomputing cluster, right? And a lot of times, you often share a very big cluster with a lot of other groups, a lot of other, people running simulations. And so it was always very annoying. So I worked in fluids, and so I worked on clusters that kind of dedicated themselves to fluid mechanics simulations. It was always extremely annoying when the people that's doing turbulence research have a conference coming up, because that means everyone that's doing turbulence research is trying to run simulations on the cluster. And turbulence research is very notorious for having very expensive simulations, like simulations that literally take 3 weeks to run on like a supercomputing cluster with thousands and thousands of computers. So, and so it was always very easy to tell when I submit a job and it doesn't run for 3 days because the turbulence people are taking up the entire cluster. It's like, oh, there's a turbulence conference coming up and they need results. So yeah, it can scale up very, very quickly. It's just, it's kind of unfortunate that we don't get a good sense of that in this class because the ANSYS licenses are kind of very. Okay. Any questions on this so far? Yeah.
I know that this is a school like version of the program, so like something like a fluid, you probably wouldn't run because element count's just way too low.
Exactly. Yeah.
Like, is there like a computer, like just like a conventional PC? Like, so like on a tight rocket, I want to do a CFD on the rocket. Is that like reasonable to be able to do that on a normal computer?
It depends on the nature of the simulation. So CFD, the world of CFD can scale up and down very, very quickly. A lot of it depends on how much turbulence is that you expect in your flow. But if you were to do something like that, I wouldn't use ANSYS. And so there are a lot of other free open softwares that you can scale up the number of elements, without limits. So
We use OpenFOAM.
OpenFOAM is the best example. And so OpenFOAM, I think, is probably the most respected, at least in the community of CFD, in terms of a free software that does so many different things. So well. The community on OpenFOAM is really good. They're very helpful in terms of helping. Any other questions on this? Okay. All right, so how do you find this balance, right? And so we've kind of talked about two factors, accuracy and computational cost, how they're kind of competing with each other. So how do you find the balance between these two? And so in FEA, what's very common in an FEA study is to do something called a mesh convergence test. And so with the mesh convergence test, this is basically a test to show, how accurate your simulation is relative to the number of elements. Okay. Because even though we know that the accuracy of your simulation will go up, as you make your elements smaller, there is a point where you kind of get negligible returns for your extra work. Okay. And so, there's usually a point where if I call it the convergence point, where if you increase the number of elements, or in other words, if you make the elements smaller, you don't get any appreciable increase in accuracy. And so to find that convergence point, usually you want to have your mesh ideally kind of around that convergence point, because that's kind of what's going to give you the most, I call it, the most bang for your buck, right? And so it's going to give you the highest amount of accuracy for the lowest amount of cost. And so to run a mesh convergence test, you're going to produce a line plot that looks like this, okay? And so there's a few ways to present the mesh convergence test results, but I usually prefer something like this. So on the horizontal axis, we have the number of elements. And then on the vertical axis, we have some marker, we have some assessment for the accuracy of your simulation. Usually it's some kind of quantity of interest. So it's for a lot of our simulations, it's going to be the structural stress or equivalent stress at some point in the structure. But really, it could be anything. It could be the strain, it could be the deformation. Whatever you're most interested in your simulation, you can put that on the vertical axis. Okay. All right, and so to run the mesh convergence test, what you're going to do is you're going to run multiple simulations under the same conditions, so same boundary conditions, same material properties. The only thing you're changing is the number of elements in the mesh, and so you're making your elements progressively smaller. And then what you're going to do for each of those simulations on each of those meshes, you're going to record, what the value of your quantity of interest is going to be. And so ideally, you should get a plot that looks like this. Okay? So each point that I'm drawing here, each data point, that's a separate simulation. Okay? So I drew a lot of points there. Sometimes a lot of times you don't have to run that many simulations, but the more data that you get, the better. Okay? And if you connect all these dots, you should hopefully reach a point where this plot is going to plateau, where it's going to flatline. And so for this plot, I would say that point is right here. And so this right here is the convergence point. And so this tells you that what this tells you is that if you increase the number of elements past this point, then you're not really going to get any improvement on the solution. You might get a very tiny amount of improvement, but it's usually not worth the effort. Okay, right? Because if you look at kind of where this point is, right? And so remember, the horizontal axis here refers to the number of elements. But remember, the number of elements, another way that we can think of the number of elements is as the computational cost of the simulation. Remember, as the number of elements goes up, so does your cost, right? And so all the data points to the right are more expensive to run than all the data points to the left. And so what the point of the mesh convergence plot is to show is that if you run a simulation at this amount of elements, or I would say at least that amount of elements, then you maximize the amount of accuracy in your mesh as much as you can. Yeah.
Could you get to a point where running your simulation, you'd run out of memory and then the simulation would fail, or
Yep.
would it still?
Oh yeah, that definitely happens. It doesn't happen a lot with ANSYS because ANSYS has a lot of safeguards in place, so that doesn't. At least if it's going to happen, ANSYS will stop you from running the simulations. But if you're using kind of a more researchy software like OpenFOAM, then that happens a lot actually. It happens just because it's hard to kind of account for all the different types of memory functions that can occur. Yeah, so for any kind of practical finite element study that you're going to do, A mesh convergence test is almost required, because one thing that people are always gonna ask you when you present computational results is they're gonna ask you, are your results converged? Did you have enough elements in your mesh, right? And the way that you can show that you had enough elements in your mesh is to have a mesh convergence plot, right?
So you're saying sometimes it takes like up to 3 weeks,
Yeah.
so then you still have to run more elements to see if you still get more accurate.
Great question. Yeah, so if you're gonna run like a very expensive simulation, then you can't run a mesh convergence test like this for every single case. And so for those cases, what they do is that, usually you're gonna run if your simulation is that expensive, you've probably run similar cases in the past, or you've run mesh convergence tests on other cases that are similar, and you kind of use that as a benchmark. And you say that, you refer to a previous study, so that in my previous study, I may have run the mesh convergence test there. And I saw that, 500 million elements is converged, and so we're gonna use approximately the same amount of elements here. Yeah. Yeah, so for those types of simulations, the convergence test is a little bit different, but you should have some data to show that it's converged, whether it be from your own study or yeah, this is something I'm gonna make you guys do too, probably not for the activities, but for the projects for sure. You're gonna have to do a mesh convergence. All right, any other questions on mesh convergence tests? All right, so let's go ahead and move on. So that's everything about element shapes, or at least element size, that I want to talk about for now. Let's talk about shapes. So like I mentioned earlier today, it's really important for the FEA, for ANSYS or for any FEA, that it knows the dimensions and the type of shapes that you're going to use. Okay, and so with that in mind, the actual amount of shapes that you can use for your mesh is often very limited. It's limited, but we still have some choice. Right, so there is some choice that you can have, but they're often very limited to certain shapes. Okay? Because in theory, you can do FEA with any element shape that you can come up with, right? You can even do, technically you can do finite elements with, a shape that has 20 sides. So if you're a D&D fan, you can make 20-sided dice FEA if you really want to. That would be a nightmare to program, but technically it's possible. And so, generally, the more complicated your finite element shapes are, the more complicated it gets to program. So usually these shapes are going to be fairly simple. Okay? Specifically for ANSYS, there are two kind of categories of shapes that you can use. And so the two categories are the triangular elements, or triangular element shapes, and the rectangular. And each of these have their corresponding 2D version and a 3D version. Alright, so let's go over the triangular shapes first. So in 2D, a triangular 2D shape is just a triangle. So it's 3 vertices and 3 sides. Okay. And in 3D, the triangular element that we can use is called a tetrahedron, which is a 4-sided pyramid. So a tetrahedron has 4 sides and four vertices. Okay, so for the rectangular elements, the 2D version is something called a quadrilateral. A quadrilateral, almost think of it as just a fancy name for a rectangle, but a quadrilateral is more generic, and so you don't have to have parallel sides necessarily for a quadrilateral. Okay. And then the 3D version of a rectangular element is known as a hexahedron. And so hex meaning 6, so there are 6 sides. This shape. Right, but sometimes, hexahedron is kind of stuffy to say, so some people will call it a brick element or a box element because it's the shape of a brick. Okay. All right, so those are the main types that you can use. So in activity one, we did 2D simulation, and so you had the choice of either triangular or quadrilateral elements. And then activity 2 will be a 3D simulation, so we'll be able to use tetrahedrons and hexahedrons. Okay. All right, so what's the difference between them? And so triangular elements are, I always tell people, is a good starting point for, if you're trying to mesh something for the first time. And the reason for this is that triangular elements have this unique property that it can mesh any geometry without failing. And so no matter what, if you use triangular elements, you will be able to produce a mesh without, and there's basically 0 chance of it failing. And so if you have a rather complicated looking geometry that you want to run FEA on, a triangular elements, tetrahedron triangles are always a good first choice to do, because at least for sure that you're going to get a mesh out of that element shape. Okay. The downside to this is that it can be very inefficient in terms of filling space. And so what that means is that, if you were to use triangular elements for a certain geometry, it's going to take usually a lot of elements to fill that space. Okay. And as we know, the more elements that you have in your mesh, the higher the cost is going to be. So triangular elements, good first option, they're safe, but they can be inefficient and drive up your costs if you're not careful. Rectangular elements are kind of the opposite of this. So rectangular elements are much more efficient at filling space. And so for a fixed amount of volume or fixed amount of geometry, if you were to use rectangular elements, it'll fill the space with less elements, okay? They also have better solution properties, and so when you approximate the solution on a rectangle, it actually gives you a better result than a triangle. It's a little bit hard to kind of explain why now, but we'll definitely go over it later in the class. And so element by element, one rectangular element is more valuable than one triangular element, both in terms of filling space and giving you a better solution. Okay? The downside to rectangular elements is that it can sometimes fail. Right. The reason for that is that when you measure geometry, what the computer does is it runs an algorithm to basically see how can you fill this space with this particular shape. Okay, and so the algorithm that triangular elements use is very, very safe and very almost foolproof. But rectangular elements, because they have a different shape, different number of sides, it uses a different algorithm that's not as reliable. So sometimes what you'll see is that if you try to measure geometry with hexahedral elements, ANSYS will just give you an error, say that it wasn't able to do this. And of course, it's not very helpful in terms of what it tells you. It just tells you that it can't. And so hexahedral elements will sometimes fail, but if you can use them, then they're generally more preferred. And sometimes it's impossible to kind of explain why they work or not. And so, some of you will experience this on Thursday. So so activity 2, I've run a few times, actually quite a few times over the last few years. And one thing I always tell people is to try meshing it with hexahedral elements. And so for the majority of the class, I would say 90% of the class, it'll work. But you'll literally be sitting next to someone, you'll have the exact same geometry, the exact same element size. Your friend will be able to produce the hexahedral mesh, but you will not. And I have not figured out why, because I guess it's just some of these computers are different, and so sometimes it's kind of random like that. Yeah.
Would increasing the element size make it work instead of fail?
Yeah. So for those cases where it is failing, if you actually reduce the element size, so you make the element smaller, that's actually what helps. Because part of the reason it fails is that it tries to fit like a box or a rectangle into kind of a weird space. But if the element is too big, it may not be able to fit into that space. But with that said, there's other things that the mesher can do, and so. But generally speaking, if you make the element smaller, it'll make it easier to mesh with the rectangular elements.
Is the measure able to use both triangular and rectangular elements in it?
It is, yes, and so for those cases, you can use mixed mesh. So you can tell the mesher to mesh certain regions with rectangular elements and certain regions with triangular elements. And later on in the class, we'll be able to tell which areas would be better suited for triangular elements, which areas would be better suited for rectangular elements. Yeah. Any other questions on element shape? Yeah, we'll definitely revisit shape a lot more this class, just because it's a very rich topic. I'm kind of simplifying it a bit now, but just as you're getting started, this is, I think, kind of sufficient to know. Okay, last thing I want to go over today before we sign off is this concept of skewness. Skewness is you can almost think of skewness as a measure of kind of how weird the shapes look, which is, I know, a terrible description, but let's dive into it a bit more. Okay? All right, so no matter which element shape that you use, whether it be triangular elements or rectangular elements, there's usually a base form, or there's a form for those elements that is ideal. Okay, and so ideally, the elements that you produce in your mesh should be as equilateral as possible. And what that means is that the lengths of the sides, the interior angles of the elements, the size of the faces, they should be as equal as possible. Right. So for example, an equilateral triangle, something like this. So this is beautiful. And so if you were to produce a triangular mesh on your geometry, and most of your triangles look like this, then that's peak FEA right there. That's as good as you can get. Okay. And so the nice thing about equilateral elements is that this will give you kind of the best solution properties, and so you're less likely to have things like the stress blowing up or things like that. What can happen sometimes is that if you're not really careful with your mesh size, then you could get very skewed looking elements. So one example of it could look something like this. And so skewed elements are ones where may not be as nice. So one good example is that maybe you have one side or one side length of your element be much shorter than the others. So maybe instead you have a triangle that looks like this, where you have two sides that are very, very long and one side is very, very short. So you want to avoid elements that look like the one on the right as much as possible. With that said, some degree of skewness is unavoidable, and so no matter unless you're running your FEA on a literal rectangle or a literal triangle, you're going to have some skewness in your mesh. But at the same time, you want to try to limit it as much as possible. Okay, at least on the interiors of your mesh, you want to have as good quality of elements as possible. Okay, so how do you test for skewness? And so ANSYS has this ability to test for what it calls element quality. And what quality does is that after you produce your mesh, ANSYS will go to every single one of your elements and kind of give it a score. Okay. ANSYS will actually have multiple different measures of quality, but I focus on skewness because I think that's kind of the easiest to visualize. Okay. And so when you ask ANSYS to measure skewness, every element will be given a score between 0 and 1. And so if your skewness is around 0 or close to 0, and so 0 skewness is good. So that means your element has very little skewness and thus will give you a good solution. This is good. Skewness of 0 is good. Versus the skewness score of 1 or close to 1 means your element is highly skewed, and so that's bad. Okay, so you want to avoid. All right. So ANSYS will go in, it'll rate all your elements, based on its geometrical factors, based on, it takes the ratio of the different side lengths and whatnot. Okay. And of course, if you have a mesh that has, 40,000 elements, or even more than that, it's impossible to go in and look at the scores for each individual one. And so the way that ANSYS actually reports this to you is that it gives you a histogram of skewness. And so it looks something like this. So, it'll give you different bins. So maybe if this bin will be like 0.0 to 0.2, 2 to 0.4, 4, 6, 6, 8, 8, 1. And then it'll give you, the size of the bins. Okay. Where the size of each bin tells you how many elements are in that category. Okay. And so for this particular histogram, we have a lot of elements in the low skew, so 0.0 to 0.2. And so this tells us that this mesh is fairly good quality because at least the majority of our elements have very, very little skewness. Okay. So what can you do if you have highly skewed elements, right? And so if you have a mesh and you have a situation where you're getting a lot of highly skewed elements, the first question you want to ask is, how do I fix this? How do I make my elements more or less skewed? And so one thing you can try is you can use this feature to kind of have ANSYS show you where most of your skewed elements are. So usually a lot of the skewness usually occurs in a very kind of clustered area. Usually in the places where your geometry does some kind of weird turns that has some sharp angles. And so you can try to refine the mesh or make the elements smaller in those problem areas. Or another thing you can try is you can try different element shapes. And so you can try to see if you can get rectangular elements. Usually rectangular elements they tend to be less skewed than triangular elements when they work. But this tool is really useful because ANSYS not only tells you how many elements are skewed, they can tell you where they are, and so that can give you some hints in terms of where you can improve your question. So this figure obtains good skewness. So yeah, so if your skewness looks something like this, so if you get a histogram that looks like this, where most of your elements are kind of in that low skewness category, that's pretty good. Right? And so, unless your geometry is very simple, you're going to have some elements in this category right here, and that's kind of unavoidable, and that's okay. But you want to try to avoid situations where that one isn't short. Yeah. All right. Any final questions on this before we wrap it up for today? Yeah.
Just kind of clarify from earlier, the element size, is that like specifically internal area of that specific element?
So the what you specify for the element size is actually the edge length, and so the length of the edge. Yeah. Specifically the maximum edge, because what the mesh is going to do is that it's when you have kind of weird parts of your geometry, it kind of has to contort the elements to get into those areas. But you can specify the maximum edge length for the element so that it kind of places a limit on the maximum size limit.
So that's what we're setting is the max limit.
Exactly. All right, so that's all we got time for today. And so on Thursday, when we meet up again, we're going to be doing our next activity. And so I'll be posting the activity tomorrow morning. So if you want to take a look early, you can. But it'll be in the same style as the first activity. So we'll be doing a lot of walk through together, and then I'll give you guys some time to work on it. Okay. All right, so thank you guys for coming today. I hope you guys enjoy the rest of your day, and I will see you on Thursday. Okay.
Thanks to guys with home. While I was writing.
Exhausted.
Oh, I did.
Everything like all those, it's like, you know, the guys just on, right? I'm on the big brain, right? I'm on
And then it's just my area with a handy.
Good.
I want to ask you.
5 hours doing it, you take a picture. Do it.
Insert
Your
part.
handy.
There it is. I wanted to like kind of run it about this. Pretty down low. What kind of things I was expecting?
It's not like crazy loud.
Yeah, I mean, that's kind of a case by case basis. So what kind of part are you looking at?
So it's a lot of labor.
Yeah.
A few more R6 with the same exhaust.
Okay.
So essentially a piece of plate, yeah, and 4 bolts for the bolt. Then I'm having a like a cylinder shaft coming off on to which the suspension would sit on.
Okay.
So there would be shear this bolts and then unload on the.
Gotcha. Okay, I think probably would be better, so I do have to run a little bit early today, but let's, yeah, if you wanna bring the part on Thursday.
Cause I'm just so that.
Yeah. I'm like, what's the season?
Right.
Getting hang just.
Right. So generally speaking, you know, if you're, it sounds like it's a component of a bigger, right? And so generally for those cases, you know, you're looking at, you know, wherever it kind of interacts with outside stuff, so wherever the bolt is something else, wherever it's, you know, being acted on by something else, you want to put some kind of boundary condition, either a right or a low. And so I think probably the most basic thing you can do is just kind of limit yourself and just fix constraints. Or fix constraint basically means that part's not gonna.
Yeah.
That's usually for, you know, where this part is something. And then the forces, that's anything that, for the modes, I would just restrict yourself to just a simple force mode. And then you would apply those to the location where you have something external. Acting on that part.
Would you rather test it part by part or as an assembly?
So, first, ideally, you know, you would do it as an assembly, so that just because the interactions between the parts usually is pretty complex. And it's hard to kind of boil that down into just a simple boundary, which is essentially what you have to do. But the issue that you're running into on assembly is the cost. And so specifically for this, for these computers, is the amount of element. So, you know, the more parts that you kind of add to the assembly, the more kind of volume you give it. You know, you have to give it more elements in order to have it be.
Kind of what we were just talking about today.
Exactly.
Okay.
And so, you know, with these, if we had, you know, a supercomputer with commercial license, I would say just do the whole assembly. And just kill it with elements, just give it 1 million elements and you know, we'll see what happens. Then you know for sure, because then all the interactions will be simulated. True. Exactly, but we can't do that. And so, you know, realistically, you're gonna have to do it component by component, just to kind of keep the cost in.
Yeah. Thanks for good practice.
Yeah, it does.
Yeah.
But yeah, bring the part on Thursday and then
Yeah, for sure.
I have some time after class Thursday, then we can take a look.
Okay, cool. Yeah, I've got like a real head start on this.
Nice. Good.
So someone's gotta get their hands on first, so
Right.
I'll be the expert.
Yeah.
Now.
It's good to work on that kind of throughout the class and so that you know, as we kind of pick up stuff in class and you can apply that.
Okay, so then also too, I asked Robinson about help. So I'm really things with the design.
Okay.
So maybe there's a.
Sure. Yeah.
Okay.
She didn't let me know. She didn't tell me. Oh, right.
She looked at me, she goes, she kind of.
I see. Okay, yeah.
So I,
Sure. I mean, I'll help with whatever I can. So,
yeah, thanks. All right. So, yeah, I guess I'll show you more things.
Okay.
Thank you.
Sounds good. Yep.
All right, have a good night.
Ethan, any final questions before I wrap it up? Okay, all right, see you Thursday.